Okay, before we look any closer at Lenz's law, I want to talk about what are the three ways that the flux can actually change through any kind of a current carrying loop. Okay, so if we look at our flux equation, remember our flux equation says magnetic flux, phi, or phi, Greek letter, equals BA cosine theta. In other words, magnetic field, area of the loop, or square, it could be really any shape you want, right? Whatever that area is, times the cosine theta, which is the angle that the area vector makes with the magnetic field. Okay, so what are the three ways that we can change a flux through this loop? Well, very easily, right? We see that there's a variable B. So we can change flux by changing the B field. So in other words, let's suppose that we had a little dial and we could turn up the magnetic field or turn down the magnetic field, right? That would change B. Okay, that would change flux. That's one way to change flux. Okay, that's, in other words, one way to induce a current. Okay, we could change the area. What if we could somehow expand or contract or squeeze together this little loop? We would then be changing the area. That's another way to change the flux and thusly to induce a current. Okay? Now, what happens if you change the angle? Well, if you change the angle, you would also be changing the flux, right? So if I just rotate this thing, that's actually how most electromagnetic generators work, is actually by changing the angle. So if you change the angle, you will also change the flux of the magnetic field moving through some coil or some current-carrying loop, and therefore induce a current that could be harnessed as electricity. All right, so three ways. So be on the lookout for any of these three possible ways that flux could change, because all three of them would induce a current in the real world or in some problem that you might get. Okay, and so I also, on the next slide here, want to briefly go over a summary of how you would approach every Lenz's law problem that you see. Okay, you could think of it as a four-step process. Step one, determine the direction of the magnetic field to begin with, right? Okay, that's going to be the direction of the flux, all right? Two, determine how the flux is changing. Is there more flux going in this direction or less flux going in that direction? Is the flux actually changing directions? Because depending on how that flux changes, that's going to influence the direction of the induced current. And then from that change in flux, step three, you could determine the direction of the induced magnetic field that will oppose the change in flux. So if there's increased flux, the induced magnetic field will point in the opposite direction of the applied field. Okay? If there's decreasing flux, the induced magnetic field is going to point in the same direction as the applied field, because you want to get it back, you want more of it, right? And if there's ever a steady flux, there's no induced magnetic field, there's no induced current. Okay? And then lastly, step four is based on what direction of the induced magnetic field you want. That's going to determine the direction of the induced current that creates that field. In other words, the field that opposes the change in flux. Okay? So let's ground this in reality by doing a few examples right now. And if you look at here, the first example says, what would be the direction of the induced current in this situation where we have, a magnetic field moving away from you. So I'm going to make this here. Magnetic field moving away from you. All these little X's. Okay. And in that magnetic field, you start out with a nice little loop of conductive wire, right? And then you squeeze it, right? So you squeeze it. Right. So if flux, again, is equal to B, A, cosine theta, we want to ask ourselves the question, which of these three things is changing? Okay? Well, if I squeeze this loop, I'm going from a big area to a little area, right? Okay, so in other words, the A is changing. So now, is this a decrease in flux or an increase in flux? Well, it's going to be a decrease in flux, right? I go from all this nice magnetic field coming out, to now less magnetic field, right? So in other words, this current carrying loop, it doesn't have a current yet, but as soon as you squeeze it, it suddenly panics. Again, it says, I want more flux this way. I want more flux this way, right? So what direction of a current will give you more flux in this direction? Well, it's similar to the example we did in the last case, right? You want the current, the magnetic field to be coming out and around and in this way, right? In other words, this way, and that will be done with a counterclockwise current, okay? A counterclockwise current, right, will give you a magnetic field that curls around in here and then back out around the other side, okay? And it doesn't matter where I do that. Let's say I do it this way, right? Thumb in this direction, that means the magnetic field is going to go in here and out around here, so that'll increase the flux coming out so that it's like it was before, and it takes a counterclockwise current to do that. Okay? That's example number 2. Let's do example number 3 over here. Okay? In this case, we have a magnetic field going towards you. Okay? We have a magnetic field going towards you. So here, it's going to look like this. This is magnetic field this way. Okay, and now let's say that I have a little half loop, right? It could be any shape you want, right? And now I'm pulling this out so that, eventually it's completely out of the magnetic field. Okay, what 3 things are changing here? Which of these 3 things are changing? Well, it goes from a lot of B field, in this case, to no B field here, right? So B is changing. You're actually changing the amount of B field that's moving through there. So the flux is changing, right? And so is that flux increasing or decreasing? This is another example where the flux is decreasing. It used to be all in, and now there's nothing in. So it wants it back, right? It wants that flux back, right? It wants some magnetic field that, again, looks like this, right? Well, what direction of current would create a magnetic field going back out at you? Ooh, look at that. It would be a clockwise current. It would be a current in this direction, right? So it would keep on going, right? I, right? You would have a clockwise current because a clockwise current, right, will create a magnetic field that's in here, comes in and around and comes out again. So on the other side it would be X's, right? Because remember, the magnetic field lines are always loops. They always connect back on themselves, but we care about the flux on the inside. In the inside, a clockwise current would have a flux going back in that makes it like it used to be, and the boomer is happy. Okay? I hope that makes sense. Okay, so let's go to another one, a little bit of a trickier one. All right, this one, we have 2 sets of coils, okay? Remember, coils, there's a name for them. They're actually called solenoids, and solenoids will also create magnetic fields. So let's say that I have some sort of little thing that hold the shape, some cylinder to hold the shape. Iron is usually the best if you're trying to make strong magnetic fields, right? And then I got some wires, right, that looks like this. Okay. All right. And that comes back down around here. There's a little switch, right? Then I have also a battery here. Okay. And so on this side, I have, I'll just do it a different color just to make it a little bit more clear. Let's go with this color. Okay. Then over here on this side, I have, it comes around like this. And this is an ammeter. Okay. So you have like a little dial, plus side, minus side. And we want to know what direction will the current be moving through the ammeter? Will it be moving this way or this way? Okay, all right. This is interesting, right? All right, so the first question to ask is, so in other words, right now, there's no magnetic flux, right? The switch isn't even closed. There's no current moving here. No magnetic fields are being made. No fluxes, right? It's a beautiful, simple world, okay? But the second that I close the switch, right? I close the switch. Now, this is the positive side of the battery. That means I have a current that's going this way, right? And that means the current's going to go this way and this way, right? And so if that is the case, right, right-hand rule says that I point my finger in the direction of the current, which means there is going to be a magnetic field now suddenly coming through this way, through these loops, through the solenoid, right? So that's going to create a magnetic field in this direction suddenly, right? And as you know, magnetic field lines, they go up and around and around and around and come back in, and they're all connected loops, right? This will go around, 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 come back in, right? So now all of a sudden, this coil here has a new flux that it didn't have before going this way, okay? And this wire says, hell no, I don't want that. I liked it better when I didn't have a flux. So it wants to now oppose this increasing magnetic flux, right? Okay, so that means this solenoid, right, is going to induce a current. So it gets a magnetic field in this direction that cancels out this new magnetic field that it doesn't like. Okay, so what direction of a current is going to give you a magnetic field in this direction inside the solenoid? Well, I want the magnetic flux, the magnetic field to be this way, right? This way. So it would be a current that's coming down or down over on this side and then allowing me to have a magnetic field in this direction. So in other words, the current would be down, down, down. That means it would follow through here from this way to this way. In other words, that is from right to left, back up, around, down, down, down. That, once again, is going to create a magnetic field through this solenoid in this direction, and that magnetic field will cancel the new flux due to this battery that was coming this way. And now it's happy again, so at least for a little while, there will be a current flowing in this direction so that through the ammeter, it's going to flow from right to left, or in other words, positive to negative. All right. Whew. That is Lenz's law. Now, on the next slide, I have all the possible scenarios for changing fluxes and what those induced currents would be. I'm not going to go through each individual one, but I encourage you to study this slide and just see if you can make sense of it. So for all the possible changing B fields, what would be the direction of the induced field and the induced current that would create that field? All right. Now, we have more examples of Lenz's law at the end, which we'll go over. Inside your book and online, there are millions of examples of Lenz's law problems. Practice them. They don't take long, and there's no math, as you can see, right? That's the kind of the beautiful thing about this. Absolutely no math, so don't stress out about that. You can solve them, each of them, in like 2 minutes, okay? Once it's one of those things where it's almost like when you look at those like 3D pictures where like the image pops out, as soon as you get Lenz's law, you get it. Like the image pops out and it's like clear and simple and you got it, okay? Sometimes, just like with the 3D images, it takes a little while to get there, but once you're there, it's good. I totally encourage you to reach out to me if you have questions, because this can be tricky. I, of course, will be available in office hours, and I hope to see you there. In the next video, we're going to take this to the next level, where instead of just talking about the induced current, we're talking about the induced EMF, or the voltage of what's called Faraday's law. And this actually will tell you what is the voltage induced inside of these circuits when there's a changing flux. And I'll see you there.